These are the AP review questions from our chapter 16-17 review. Now a quick little remark. These are actually among some of the toughest AP questions I've seen from the multiple choice, so get ready for some confusion, but let's try to get some of these concepts applied that we've learned about. So let's begin with number 15. Here we have three equations. Now you'll notice that the equation shows this acid, which is phosphoric acid, which is a triprotic acid. It has three ionizable hydrogens, and it shows the process of each hydrogen being given off, along with the corresponding Ka. So we have phosphoric into H plus and its conjugate, then we have that conjugate into H plus and its conjugate, finally that conjugate into H plus and its final conjugate. The question is this. A solution is prepared by mixing 50 mils of sodium hydrogen phosphate, which gives us this compound right here. Let's get rid of the rest. So sodium hydrogen phosphate actually produces that compound, with 50 mils of 1 molar sodium monohydrogen phosphate. This is dihydrogen, so half and half of this. So we're actually putting together half of this and half of this into the solution. And they're asking which of the following species is present in the lowest concentration. So the idea is Na is out right away because Na came with both of these, so Na is fully ionized. And then when we put H2PO4 in the system, it partially ionizes into HPO4 2-. Now it very partially ionizes into this because the Ka is a pretty small number comparatively. But then since we put a bunch of HPO4 in the system directly, it ionizes into its conjugate, producing a tiny, tiny amount, really tiny amount of this because the Ka is so small. So this right here actually is a species in the lowest concentration because the corresponding Ka of this acid is the smallest. So that's really the answer. Sort of think through it, and this is a reflection essentially of what an equilibrium constant tells you. All right, let's go down one. Let's do number 10. Here we have an acetate buffer solution. By the way, the previous one I should have said is also a buffer. Was a buffer because we put the two conjugates. Here we have another conjugate from acetic acid, which is very common. We're putting 50 mils of 0.2 molar acetic acid, which is this substance, and 50 mils of 0.2 molar sodium acetate, which is its conjugate. Again, notice sodium is bringing these conjugates into the system. A 5 ml sample of 0.1 molar sodium hydroxide of base is added to the buffer solution. Which of the following is the correct pairing of the acetate species present in greater concentration? So we want to know which do we have more of, this guy or this guy, along with the pH of the solution after the addition of the NaOH. Now, we're told that the Ka of acetic acid is such and such. So we want to know if we have the regular acid or we have more of the conjugate, along with if the pH is basic or acidic. This is less than 4.7 would be acidic, this would be basic. Well, close. So if you take a look, we're putting an equal molar amount of this guy with this guy. So 1-to-1 mole ratio because we're putting the same molarity with the same milliliters. So when you add sodium hydroxide to the system, the hydroxide, which is a base, interacts with the acid. And then the acid is converted into its conjugate. So in fact, we lose some acid, we gain some more acetate. We lose acetic acid, we gain more acetate. So sodium or acetate actually increases. So we in fact have more acetate. So we're between now C and D. These are out. The question is the pH less than 4.7 or more than 4.7? Well, because we've added a base, which neutralized an acid, and then produced more conjugate base, we actually have more conjugate base, so the pH has went up. So in fact, the pH is higher than 4.7. D is the correct answer. Now, we're not quite basic, but we are higher than what we began. And by the way, they're using 4.7 because the Ka is 4.7, and when you put equal amounts of the acid and the conjugate, your pH equals to your pKa. That's the idea. All right, let's turn it up a notch. Let's do this one. Let's do 37 on the right side. So here we have two acids, and along with their Kas. And that's what they're told us. The Kas of this acid and this acid are given in the table above. Which of the following mixtures is a buffer with a pH approximately of 3? So we want to create a pH of 3. Now, the pH of 3 is going to probably be connected to the Ka, kind of like the previous question. The idea is the pKa of this is going to be pretty close to 3. I know that because this is 8.3, which is almost 10 or close to 10, which gives this to the negative third. So this is about 10 to the negative third. So I know if I take the negative log, which is what pKa does, I'll get roughly 3. So in order for me to get pH of 3 in a buffer, I have to have equal molar amounts of him and his conjugate. So I have to have him plus his conjugate in equal molar amounts. That will give me a pH close to 3. And I should maybe explain it in terms of the buffer equation. So remember, the buffer equation said pH is negative log, or pKa rather, negative log of Ka, which is pKa, plus log of base over acid. Now, when you have equal molar amounts of the conjugate base and the acid, which is what this turns out to be 1. If you take the log of 1, you'll get a 0. This can be a 0. And essentially, this term crosses out. Your pH is equal to your pKa. So when your amount of acid and conjugate are equal, the pH equals the pKa. That's where that comes from. All right, so if we mix, A says we're going to mix 100 mils of our first acid, which is probably what we want to get a pH of 3, and 50 mils of sodium hydroxide. Now what that would do is it would convert half of, wait a minute, I'm lying. This is actually the second compound. Read it carefully. This guy right here is him, so read it carefully. Whoops, almost throw us for a loop there. So this actually is not what we want. We want the other compound. This one's out. B says a mixture of 100 mils of, oh, this is our man, if it's a man. This is what we want. Good, that's connected now. With 50 mils of sodium hydroxide, yes, because 50 mils of sodium hydroxide will take half of him, half of 100, and convert half of him into the conjugate. So then, yeah, that should do it. So because then we'll get half of him converted into a conjugate. If we use the whole amount, all 100 mils, then all of him will be converted to a conjugate. We don't want that. Good. So very nice. So this should do it. Or B should do it. All right. Again, these are tough. You're probably thinking along with me, these are pretty noxious. All right, how about the top one here? Go up to the top. Here is another acid-base type question. Here we're told to maximize the yield in a certain manufacturing process, a solution of a weak monoprotic acid that has a concentration between 0.2 and 0.3 is required. So we need a 0.2 to 0.3 weak acid solution. That's all they're telling us. 4 100 ml samples of the acid at different concentrations are each titrated with a 0.2 molar sodium. So it's the same acid, except we're doing different samples at different concentrations against a 0.2 molar sodium hydroxide solution. The volume of sodium hydroxide needed to reach the endpoint for each sample is given in the table above. Which solution is the most suitable to maximize the yield? So the more base it takes to neutralize it, the stronger the acid was, or the more concentrated rather. I shouldn't say the stronger. It bears noting that if you have, say, 0.1 molar or 0.1 moles of a weak acid, and if you have 0.1 moles of a strong acid, the amount of base that will be necessary to neutralize both of them is the same. You'll actually need 0.1 moles of base, as long as it's monoprotic all around. So it doesn't matter if you have a weak base, a weak acid, you still need the same amount of the weak base for it. So bearing that in mind, this would be the highest concentration. This would be the lowest concentration, because this took the most acid, this took base, this took the least. Now what we want is we want a solution that's between 0.2 and 0.3. If we were to use exactly the same amount, then our solution would be 0.2. Like if in here, if one of the entries was 100 mils, then we know that this acid, whatever that was, would have been the 0.2 because it matches the 0.2 of the base. Notice. So, but we want it to be between 0.2 and 0.3, which means we want a higher concentration, which means we should have used more base, which means C is the answer. Solution C. Again, solution C, because it took a little more base to react with it, which means it's a little more concentrated than 0.2, since we're using the same molarity, or the same amount, rather. So hopefully that one makes a little more sense. All right, let's go to the last one, which is the most confusing of all. Which of the following accounts, this is number 30, for the fact or observation that pH of pure water at 37 degrees Celsius is 6.8. Now we know that pH of pure water should be 7.0, but that's at 25 degrees Celsius. Remember, how we get this is that water self-ionizes to produce H plus and OH minus, and the relative concentrations of these equal the Kw, which is 1.0 times 10 to the negative 14. And if you square root this, you'll see that both H plus and H minus, OH minus, are actually 10 to the negative 7. And that's how we get the product of these being 10 to the negative 14. Now, we're told that at 37 degrees Celsius, the pH is a little less. What that means is that these numbers are not 10 to the negative 7, but 10 to the negative 6.8. 10 to the negative 6.8. So what we're told is that these numbers have decreased, or rather, well, we should say it's increased. Because remember, this is actually higher. Do you agree that this is higher? This number is higher than 10 to the negative 7. This is actually a bigger number. Slightly, because we're raising it to the smaller negative power, if you would. So, in other words, our concentrations have increased. Let's see which matches that. A says the water is naturally acidic. That makes no sense. Just cross that up. B says at 37 degrees Celsius, the auto-ionization constant for water is larger. Okay, that would make sense because if the K is larger, that means our numbers are going to be larger. That one makes sense. Let's hold on to it. At 37 degrees Celsius, water has a lower density. Okay, yes, it does have a lower density. It's true because when you heat an object up, it expands, the density decreases. Then it does at 25, therefore H plus is greater. No, the H plus would be less if it's less dense, right? Because density is mass over volume. This is molarity, which is moles per volume. Same idea, mass and moles are interconvertible. So if this goes down, this actually would go down, so it won't be greater, it'd be smaller. Wipe that one down. Oh, there you go. And D says at 37 degrees Celsius, water ionizes to a lesser extent than it does at 25. Okay, so this bears on the same idea. Does it ionize to a lesser extent or to a greater extent? It actually ionizes to a greater extent because our number is bigger. So this is a bigger number. We have more OH minus at equilibrium. This one's out. Okay, that was a doozy. I do agree. So try to look through some of these. These, again, are some of the toughest AP, twisted AP exam questions they can come up with. But if you can grab a hold of 1 or 2 or 3 of these, you are on good soil, good track. All right? That completes our video.